Hey everybody, the purpose of this video is to get us a more visual look at what we were looking at in class recently. The idea of confidence intervals, overlapping versus non-overlapping, and then collapsing them down to one. And I think more visuals will help us with that. So I want to start with part one, which is what happens if you form two confidence intervals that are comparing two different parameters to each other. Okay, so we're going to start with that one. So here's a number line, and I'm going to draw two overlapping confidence intervals on that number line. Okay, and we'll add numbers to it in a second. Okay, so there's one, there's two, and let's throw some numbers up here just to compare them. So let's say this and this. Just to make the math easy, I think. So let's say that this is 30%, and this is 50%, and this is 40%. Okay, so it looks like confidence interval number one looks like it's about 30% up to about 42%. And it looks like confidence interval number two is maybe 35 to 50. Okay. So what can we conclude from having these two intervals? So suppose these are two competing percentages. Suppose they're percentages that are favorability ratings for two politicians in the same district. Or suppose they are reaction rates to two different medicines for the same allergen. Something, I mean, whatever it is. They're comparing two things to each other. Okay. So what this tells us is we can't tell if one is larger or smaller than the other at the we'll come back to that in a second, statistically significantly. And the reason is this interval, 30 to 42%, represents the 95% confidence interval. What that represents is the range of values between which we believe the parameter to lie. So the way I've been having you all think of it in class is think of it as a little fish in that tank. There's a fish in that tank 95% of the time. He's in the tank, but you don't know where in the tank, just somewhere in the tank. There's also another fish in this little tank right here. Again, 95% of the time, fishy's in that tank. The catch is, since you don't know where they are, it's possible that the fish in the yellow tank is to the right of the fish in the blue tank, thereby meaning the parameter is higher in the yellow tank than the blue tank. That's possible. It's also possible that the fish in the yellow tank might be to the left and is therefore lower than the fish in the blue tank. So it's possible that the parameter you're studying in the yellow tank is higher than the blue tank. It's also possible that it's lower than in the blue. It's also possible that they're both equal. So in other words, if the confidence intervals overlap like that, there's no way of discerning which of the two parameters you're estimating is significantly larger or smaller or unequal to the other. When the intervals overlap, no way of being able to tell them apart. Okay, because we're uncertain as to where the parameter actually lies. So that's if they overlap each other. Okay, so hopefully that makes sense. I think that part made sense. And I also think that the next part would make sense. Let's create two more intervals that don't overlap. So let's use pink and purple. So let's say we've got another interval down here that goes from, say, 30 to 36, and then this one here goes from, say, 40 to 45. Ooh, that doesn't write very well. Okay. So what I want to do now is look at these two intervals. Now, those intervals are our 95% confidence intervals that are representing the tanks that we believe the parameter fish to be in. So we believe this parameter fish is in this tank 95% of the time, and this parameter fish is in this tank 95% of the time. The difference this time is these tanks don't overlap each other like those tanks did, which means no matter how far down this fish gets in its tank, it's still higher than the highest point in this tank. which means we are now confident, statistically significantly confident, that this parameter is above this parameter. Looks like there to be about a 4% difference minimally, maybe even more. That's a non-overlapping set of confidence intervals. So the difference between overlapping and non-overlapping is the fact that the fish might be in the same tank here. They can't be in the same tank here. Hopefully that makes sense. If that doesn't make sense, say it this way. Since we don't know where these two fish are in their respective tanks, it's possible one is to the right or to the left or directly on top of each other. In this situation, there's only one possible situation. Purple fish is to the right of pink fish. They can't be equal and they can't be reversed because of the position of their tanks. Now, when I say can't be, I'm speaking in terms of confidence. Each of these intervals is only 95%. So I want to come back to a second point before we move on to the last bit of this video. The second point is that in these two up here, when we looked at these two, just these two, we are no longer totally at 95% confidence. We're at 90% confidence, because if this one's at 95% and that one's at 95%, that means altogether we're at 95 squared, which is about 90% confidence. If you add two more intervals in, suppose these are four different things you're comparing simultaneously, you've now dropped to about 81% confidence. Every time you throw another interval in there, you get less and less confident because there's a more and more chance that you missed it. As a matter of fact, if you put enough intervals up there, it's almost a certainty that one of them is going to miss. That's the definition of confidence, right? 95% confidence means out of 100 such intervals, 95 of them on average are going to trap the fish. They're going to trap the parameter. So if we threw 20 intervals up on the board, on average, one of them is going to miss, because 95% means 19 out of 20, which means 1 out of 20 misses. So that's a review of confidence, a look at how you measure what's called statistical significance, but also one of the problems when you stack too many intervals up. This is why you should always be nervous, for many reasons, but here's one reason why you should be nervous during political cycles when they start having 8 million confidence intervals. Here's this candidate, this candidate, this candidate, this candidate, this candidate. Even if the data was collected correctly, which it wasn't, but even if it were collected correctly, having that many intervals almost guarantees at least one of them is going to be off. So what I'd like to look at now is what we were talking about in class yesterday, and I don't think this was super clear, so I wanted to make it more visual. A better way to say, looking at that comparison up there. So what that up there did, I'm going to erase the board here and start from scratch. When you have a single parameter confidence interval, like each of these things were, what you have is you take an average in your sample, so you take your sample average, and you add and subtract its margin of error. That's what the confidence, throwing chalk here. That's what the confidence interval looks like. It's the sample average, added, subtracted, its margin of error. So what that translates to, and I think you all kind of like the way I'm going to write it next, if you take your sample average minus the margin of error, and you look at the sample average plus the margin of error, 95% of the time, the population parameter is going to be wedged in between those two things, 95% of the time. Which means out of 100 intervals, 95 of them catch the parameter in between the two LCL and UCL values from your interval. Okay, but as we just saw, when you have two parameters you're trying to estimate, let's throw mu's in there for. So suppose you want to estimate mu1 and mu2. So don't let the Greek letters scare you. All that means is two variables. We're trying to estimate, say, the average weight of a group over here that's on a certain exercise regimen and the average weight of a group over here that's on a different exercise regimen. Or we're trying to estimate the average body temperature of these folks on a certain medicine and the average body temperature of these folks over here who are not on that medicine. Just two different values. Now we could very easily do this twice. But the problem, as we just saw, is if we do that, we end up running the risk of losing confidence. So a better way, if you have two averages to look at, is to draw the two samples, draw the sample from population 1 and population 2, and the sample average for this one we can call it X bar 1, and for this one we can call it X bar 2. So you have two sample averages now. We did this in class and y'all were okay with it, I think. And once you have that, rather than building an interval around each of them and then looking for a difference, let's reverse that order. Let's look at the difference of the two of those and then form an interval around that. And we'll say that again. Rather than building intervals around each of these things and then looking for a difference, we're going to subtract these two from each other to find their difference and then build an interval around this. So we're going to collapse this down into the statistic X bar 1 minus X bar 2. So to give you a concrete example, let's go back to that example I made up a few moments ago. Suppose we're measuring the body temperature of this group over here and the body temperature of this group over here. And we draw a sample and their body temperature is like 98.4. Their body temperature is 98.7. Okay? If I subtract those two, 98.4 minus 98.7, I get a negative 0.3 degree difference. That would be the value of this statistic. This in and of itself is a statistic. It is. It's a statistic all by itself. But it's a statistic, right? Which means it needs a 3 words. Come on now. I know you're in a computer lab or you're on your phone or you're in a restaurant or a coffee shop, but let's hear it. Every statistic has to have a 3 words added to it. Good. A margin of error. So what we need to do is take that and add and subtract a margin of error to it. We got to take that and add and subtract a margin of error to it. Now, I don't want you to worry about that. The technology will take care of that computation. These computations start getting pretty hairy once we start getting into multiple variables like this one. What I want to focus on is I want to focus on what the interval means that you get out. And I'm going to go back to this whole body temperature one because I think that's an important one. Okay, I'm going to clear the board again. I'm going to put this back at the top. I really could use more boards in here. Okay. So far we know we have to form this. To make it maybe a little more visual, I'm going to put parentheses around that. All that means is that's my statistic. Statistic plus or minus a margin of error. Okay, let's make up a value for this. Let's just make up, just to throw some numbers on the board. We just made up this value. If X bar 1 was 98 point, I think we said it was 4 degrees, and X bar 2 was 98.7 degrees, then the difference of the two of them, X bar 1 minus X bar 2, is negative 0.3 degrees. Okay, now if we were crappy statisticians, which we're not, but if we were, we would say, oh, that's a negative value. That means this sample had a lower average temperature than this one. That's how you get a negative number, right? Well, that means in the population one must therefore have a lower body temperature than population 2. And that's where you have to stop and go back and say, oh, wait a minute. I can't make that assumption. I can't make the assumption that the difference in the samples is going to be exactly the same as the difference in the population. Does that make sense? Let's say that again. The difference in the samples might not be the same as the difference in the population, which is why we need to have the margin of error. The margin of error takes care of that difference. Okay, that's what we're going to do next. So what we're going to do is we slap that margin of error. Now, I don't know without calculating it. I just made these numbers up. So let's create a margin of error. Let's say that the margin of error in our study is 1/2 of a degree. Just to throw a number in there. Okay, just to throw a number in there. Our confidence interval, therefore, is going to be negative 0.3 degrees plus or minus 1/2 of a degree. Okay, margin of error always has to be positive just because it's due to the positive square root. So, and again, don't get hung up on that. Technology takes care of that. It's the interpretation that I care about. Okay, so looking at the endpoints of this means I've got negative 0.3 minus 0.5, which is negative 0.8 degrees, up to negative 0.3 plus 0.5, which is positive 0.2 degrees. And this is where we started having issues in class. When it goes from negative to positive, what does that mean? So here, I want to bring back the fish tank. bring it back to fish tank. I'm going to put a very important number right in the middle, 0. That number is going to be crucial, and we're going to understand why as we go through this video. 0 in the middle. Okay, negative point. I'm going to make it go from -1 degree up to 1 degree. Okay, and then we're going to draw this blue. -0.8 up to +0.2. That's about right, I think. Okay, there's your tank. Now I'm going to ask a question. I want you to think about it. It's a slightly tricky question. How many fish are in the tank? Just one. Just one. Every tank has 1 fish in it. If the tank had 2 fish in it, it would be a useless tank. Because if the tank had 2 fish and they were bumping into each other, you wouldn't be able to discern which tank was which. So you might be asking yourselves, but Sean, how in God's name can there only be 1 fish when there are 2 statistics? But you got to remember something. We subtracted the statistics. So the fish no longer represents either one of these two. The fish represents the difference between them. The fish represents the difference between the 2 parameters that we're estimating. So check this out. If I put the fish in this part of the tank right here, that means the fish, which stands for the parameter difference, which we have now erased on the board, I'll put that up in a second. The fish is on the negative side of 0. What does it mean if the fish is on the negative side of 0? Well, that would mean if I was looking at the difference in parameters μ1 minus μ2, that means it's less than 0. If it's less than 0, that means this number has to be smaller than that number. So if the fish is on the left side of this interval into the negative part of the number line, that means the μ2 values must be bigger than the μ1 values. Don't overthink that. That's all it means. So, and we saw that in the sample, right? This was a sample value, not a parameter value. But you had 98.4 minus 98.7. X bar 2 was bigger than X bar 1 in that particular case. But any fish on this side would represent a parametric value where μ1 was less than μ2. So anywhere in that part of the interval. But what if the fish were over here? What if the fish were over here? Well, that would mean that the difference of μ1 and μ2 were positive. A number greater than 0. Well, what does that mean? Well, that means that μ1 is bigger than μ2. Now, we didn't see that with our sample stats. But remember, that was just our sample stat before adding a margin of error. The margin of error makes up for the fact that the sample stat is only one snapshot of all possible samples. So it's possible at this confidence level with this interval that the parameters might be on the other side of the interval, implying that μ1 is actually bigger than μ2. And here's another possibility. What if the fish sits directly on top of 0? Well, that means that μ1 minus μ2 equals 0. Which would mean, what would have to be true about μ1 and μ2? They'd have to be the same. The same. So in other words, with an interval like this, where the fish can be anywhere from the left to the right and anywhere in between, we can't tell if it's in the negative side or the positive side or landing directly on 0, not on a side. That means that this confidence interval is not statistical evidence of a difference between these two things. We can't tell. They might be, one might be bigger than the other, or reversed, or they might be equal. When you have your hands go like this and go, I'm not sure what exactly happens, we can't tell a difference. So in other words, just because the sample is less than this sample means nothing in the population at this level of confidence with this interval. So here's the dead giveaway. The dead giveaway is the fact that the numbers went from negative to positive. If they change like that and pass through 0, that means they pass through 3 ranges. On one side, one parameter appears to be smaller. On the other side, it reverses, and where it reversed, they appear to be equal. And that, my friends, is the challenge of looking at an interval like that. Anytime it goes negative to positive, it crosses through 0. Now, that means nothing statistically significantly can be shown to be different. So what would be the example of one where you could see a statistical significant difference? Okay, so not this one, clearly. Well, you're looking at what we just said. If the intervals pass through 0, then there's no statistically significant difference. Making the logical contrapositive of that means if we want to see significant differences, then make sure your interval doesn't contain 0. Watch this. I'm going to erase all this. Just leave the number line up. Actually, now that I erased all that, I'm going to go ahead and put something back on the board. We're trying to estimate the difference between two parameters, mu1 and mu2. We do that with a confidence interval x bar 1 minus x bar 2 plus or minus the margin of error. That's how we do that. Suppose when we graph that confidence interval right there, it looks like that. Fish in the tank. There's a fish. That fish is on the positive side. If the fish is over here, it's on the positive side. Over here, on the positive. As far left as it can go, it's still on the positive side. No matter where the fish swims in that tank, it's always on the positive side. So looking at the values this appears to be, it looks like it's about at 0.3 degrees, maybe up to about 1.2 degrees. Notice both those numbers are positive. If they're both positive, that means we're 95% confident 0 is not in there. And if 0 is not in there, there can't be negative numbers in there. We're 95% confident the difference is positive. If we're 95% confident the difference is positive, that means we're 95% confident that mu1 must be bigger than mu2. That would be statistical significant evidence that average 1 is bigger than average 2 in this particular case. That's it. Look for 0. If 0 is not in there, that means the entire interval is on one or the other side of 0. If it's on the right side of 0, mu1's bigger. If it's on the left side of 0, mu1's lesser. There you go. I think what was hanging you all up was we're trying to make it harder than it had to be, which is often the case with us as math students. We do that all the time, don't we? But I wanted to kind of draw this out with the fish tank some more to get you a video before next class. And hopefully it helped. If not, ask me and we'll talk about it some more. See ya.